Okay, a bit of Tchaikovsky piano concerto there. Mice are multiplying in Mossman. So this is an exponential growth question. It says it right. It says it right there. Exponential growth model. The main thing is to sort of work out what you know and what you're seeking to know at each stage. Okay, mice are multiplying in Mossman. Their population M is estimated to be 80,000 at the start of 2010 and 130,000 at the start of 2015. Assuming an exponential growth model where dm dt is km, which is just a way of saying that the rate of change is proportional to the population itself. The population is changing by a certain percentage every year, a certain percentage of the current population, increasing in this case because it's growth. Okay, where k is a constant and t is time in years after 2000. Okay, i.e. when t equals 0, m is 80,000. We're translating the information from the question. And when t equals 5, 2015, the start of 2015 is 5 years. After the start of 2010, when t is 5, m equals 130,000. Those are two snapshots you've been given. Okay, and so in part A, it says, show that m equals 80,000 e to the kt satisfy the differential equation. All that's saying is, if m equals 80,000 e to the kt, then what's dm dt? Well, dm dt is k times 80,000 e to the kt, which is km, which is a way of saying that this is a solution of this differential equation. Okay, my daughter is deciding to sing a song in her bath. Pardon me. So, n has an initial equation, initial value. When t equals 0, m equals 80,000 e to the 0, which is 80,000. So the initial value of 80,000 works. So this is true, and the initial value of 80,000, and this satisfies the differential equation. Find k. How do I find k? Well, I've got a snapshot here. What's the information I haven't used yet? This snapshot. So when t equals 5, so when t equals 5, m equals 130,000. So sub that in, you get 130,000 equals 80,000 e to the 5k, and obviously then solve for k. So that's 13 over 8 equals e to the 5k. So k equals, 5k equals ln 13 on 8. So k is a fifth log 13 on 8, which is approximately something, where's my calculator? 0.2 times ln 13 on 8. It's 0.0971. Did it give you an approximation? Correctly, no. Find k. Okay, so k, that's an approximation. I wouldn't use this approximation in my subsequent calculations. What it's saying is, now you've subbed in, the initial value gave you the 80,000, okay, and then the subsequent value here gave you the value of k. So now the initial equation, the actual equation is m equals 80,000 e to the 1/5 ln 13 on 8 t, e to the kt. That k there is a bit of a complicated thing to write, but nonetheless that is the actual value of k. You could write it as 0.971 if you like. Sorry, that's 0.0971 t, but I would urge you, small variations, small differences in this number will cause large differences in your answers at the end of the question. So I would highly recommend that you use the very long approximation on your calculator, which in this case is 0.09710156316. I would use all of that in performing any subsequent calculations. and predict the population at the start of 2028. So the start of 2028 is when T equals 8, M equals 80,000, E to the, perhaps write it as 8 on 5, learn 13 on 8. Times 5 rather. So times 5, that we already did, times 8 rather, 8. So I've already written that, so then how do I get that from my calculator? Well, in my case, I'm going to write 80,000 times E to the power of 8 times the answer I already had in the calculator, which gives me 173,000, was it to the nearest thousand? So that's 174,000 to the nearest thousand, in fact. Approximately equals 174,000. If you typed in, let's try it, 80,000. Yes. Just give me a second. I'm just recording a video. E to the power of 0.971 times 8. And I get 189,000. So that's, sorry, I made a mistake there. 0.0, that I typed it in completely correctly. 0.0971 times 8. And I get 173,960. I get a difference of about 30. Just give me one moment, Fia. I'll almost finish this question. Okay. C. Predict in what year the population will first exceed 1 million. So you're looking for basically where it was 1 million equal 80,000 E to the 1/5 ln 13 on 8 T, which is to say 1 million on 80,000, which is what, 125, is it? Let me just, 3, 4, 5, 6 on 80,000, is it 100? Oh, 12.5, not 125, 12.5. Of course it is. 12.5, 80,000 times 12 is 960,000, so it's 12 and a half. 12.5 equals e to the blah, blah, blah. So it's ln of 12.5 is a fifth ln 13 on 8t. So t is, so let's do it as 5 ln 12.5. 5 ln 12.5 over the log of 13 on 8, ln 13 on 8. Or if you've got your 1/5 ln 13 on 8 value already in there, if you've got your k already in there, which was 0.0971, you're basically doing the log of 12.5 over 0.0971. T equals that. Now, rather than typing in 0.0971, you should actually use that approximation. So that's the log of 12.5 divided by, close brackets, divided by my answer, and I get approximately 26.01. 26.011. So it says, predict in what year. So when t equals 26 is the start of the start of 2010, start of 2010, start of 2036, 2036. Therefore, during 2036, the population will exceed 1 million mice. Okay, I'm hoping that's right. You can actually test that out just by typing in 80,000 times e to the times e with the e button, shift e to the power. That's not how. Sorry, it's just a bit hard to use a calculator with a mouse. E to the power of 1/5. And I didn't. 0.2 log of 13 on 8, 13 on 8, close brackets, times, and was it 26.01, 26.01, and hopefully my calculator will give me a number, 999,000, clearly getting close to 1 million. If I just turned it to 26.1, which is obviously a lot more than 26.01, then I've got a number over 1 million. So that's worth doing on your calculator just to double check. That's chapter 16 review question 3. I was also asked question 4, but I might do that in a separate video.